Saxon Advanced Mathematics. Lesson 53. We're at the beginning of week, let's see, this is week 14, so this was week 15, right? Let's see if I got that right. Yes, we had 13 weeks before Christmas, before the break, so now we're 14, 15. Here we go. The lesson that I'm going to teach you today is a bit of a workout. It's related to physics. And so there's a lot of terminology and conceptual stuff that I'm going to tell you just enough to be dangerous. And then if you come back to this stuff in a physics class someday, you're going to be like, oh, I vaguely remember this. It'll all make a lot more sense as you see it in the future. Now, in order to do these calculations, we have to do some fairly complicated unit multiplier calculations. So before we get into the new stuff, we're just going to do a quick review. Well, it's not quick because it's actually a long problem, but we're going to remind ourselves how to do unit multipliers when there's lots of pieces flying around. So that's our first example. And what John wants us to do is he wants us to change 40 miles per hour into, and I'm going to put it in a second row because I know we're going to need two rows, meters per second. Okay, just a reminder that MI is miles and just a plain M is meters. We'll want to make sure we keep that straight, right? Okay, so we notice that we have here not just a unit in the numerator, but we have a unit that is a rate, right? So we have to change from miles to meters, and then we have to change from hours to seconds. We've practiced this earlier this year, but let's just go through it again. So what we're gonna do is first let's deal with the denominator. We're gonna need to go from miles to feet, right? We have to go from English to metric. So that means we have to crawl through the portal, which is inches and centimeters. Then we have to go from feet to inches. Then we have to go from inches to centimeters. And then we have to go from centimeters to meters, and that will get us where we need to be. So we're going to need 4 boxes to convert just the numerator dimension, to go from miles to meters. I'm just double checking to make sure it makes sense. Miles to feet, feet to inches, inches to centimeters, that's important, and then centimeters back up to meters. Okay, good. Then, this wouldn't have to be in a second row, but I just knew I was going to run out of space. Hours, we need to go to seconds. So we'll go hours to minutes, and then we'll go minutes to second. These problems are a challenge because there is just so much that we have to do. So organize your work in a way that someone else could figure out. It is very important to me that you show what you're trying to do in each box so that someone else could come along and make sense of your work. All right, here we go. Turn these all into fractions because we know that unit multipliers are fractions. We start by asking ourselves, which of these two units do we want on the bottom? We're starting in miles, so we'll put that opposite so that it'll cancel. Feet goes in the other place. Which is bigger, a foot or a mile? How many feet are in a mile? Oh, this is the big number, 5280. Okay, now we're in feet. Good, because we want to go from feet to inches. Feet down here, so it'll cancel. Inches up here. 1 foot, 12 inches. Feet, feet, cancel. Make sure that you do these problems exactly the way that I show you. Period. The end. Inches to centimeters. Inches on the bottom, centimeters up top. Inches bigger, 2.54. Inches cancel. If you don't know all of these numbers, they are listed on the first page. Let me show you in the book. Here's a bunch of them. listed here. I mean, 24 hours in a day, you probably, life lesson, you probably already know that. If you are not familiar with all of those, look on page, in my book, it is 353. It is the first page of this lesson. And make sure that you have all of those unit numbers written down and memorized. Super important. Okay, now we're going from centimeters to centimeters. I've got centimeters up here, so I'm gonna want them down there. Meters, right? We always wanna set this up so it'll cancel. I'm going a little fast because if you've been using the Saxon curriculum for years, you've been practicing these, and hopefully you remember. A meter is bigger, 100 centimeters in a meter. Remember that prefix cent? Implies 100, like 100 cents in a dollar, 100 years in a century. So this prefix always implies 100. Okay, and just similarly, the word kilo always implies 1,000. Okay, so now we are at meters, and that's exactly where we want to be. The numerator is done. Yay! That was a lot, wasn't it? Okay, now we want to convert the denominator, which is hours. We want to change the hours to minutes. That's what we're going to do here. Because hours is the starting unit in the denominator, we'll want to put it up here in the numerator so it'll cancel. Minutes will go here. Remember, we always use the 2 units that we're trying to transfer between right there. An hour is bigger. There are 60 minutes in an hour. Hours cancel, and we're in minutes. Now we want to go from minutes to seconds. Minutes are down, so we'll want them up. Seconds will go here. A minute is longer. A second, there are 60 of them. The minutes cancel, and now we're in seconds. I always write out seconds as S-E-C because my S's tend to look like 5s. And I don't want that to confuse you. In John, in the textbook, he just uses the S. But I write it out because I don't want my S's. S's are problematic for me. All right, so our final answer, we once again double check. This is just a conversion of length. It's in 1 dimension. Rates typically are 1-dimensional. And this is a rate because it is a distance over a time. That's how we can tell. Distance over a time. And we just are going to get all these pieces in one place. The original 40 times 5280 times 12 times 2.54. The one we can ignore, and then those 2 ones we can ignore. Over, and now we skim through all the denominators. Look at all those ones. Okay, there's a 100. And a 60 and a 60. Right? And then it's meters per second. Again, I'm going to write that out so it's super clear. This is the final answer. Let me just double check it, make sure it's right. That, my friends, that's a hefty little calculation, isn't it? And the reason we reviewed it is because we're going to have to do a bunch of other stuff in our problems, but this is going to be a part of our other problem. I know, buckle in. This is correct. All right, so remember the rules of this as we go on and start to talk about these unknown concepts. I'm assuming you don't know anything about them. Maybe you have had a physics class and you know something about these, but I'm going to pretend you don't know anything. And again, whenever I'm teaching science and math, I teach you just enough science so that you can know how to do the math. If I'm oversimplifying things from the scientific side, just know that that's why I do it that way. I'm not trying to teach you physics here. I'm trying to teach you how to do the math in physics, and sometimes I understate the science so that that doesn't confuse us or distract us. All right, we're talking about velocity. Velocity is a fancy word that means speed, which is usually expressed in a rate, okay? So these three words are all related, all right? The first type, we're gonna talk about two types of velocity. The first type of velocity is called angular velocity. And what that means is the rate that something is rotating. So we're going to talk a lot about wheels and tires in this one. The rate of rotation, okay? How fast is something spinning? We use a variable for this, and it is kind of a fancy W. It is omega. It's a Greek letter. We sometimes use that when we're talking about it. But that W is what we're going to use as the variable for angular velocity, which is a rate of rotation, and it's expressed as a rate, right? So it might be a certain number of degrees per second, or it could be a number of degrees per minute, okay? So we can measure the rotation in degrees, or we can measure it in revolutions per second, or revolutions per minute. That's another way. Instead of measuring the degrees, we'd measure the revolutions, right? But this is the way we're gonna like to talk about it. Rads per second, oh, radians, are you kidding me right now? Or radians per minute. I'll explain why in a minute, but these are the favored sons of this problem. We want to get our problem into radians, all right? And I want to just draw you a little picture. Let's say that this is a wheel that's turning. And let's say that there's like an inner circle and an outer circle. This point is a shorter distance from the center than this point, okay? So when the wheel goes around one circle, they're each gonna make one revolution. So these 2 points, let's name them P and Q. P and Q have the same angular velocity. As you can guess, by the way I said that, I'm gonna contradict that. I'm gonna draw a distinction in a minute, okay? So they're on the same thing. When it rotates one revolution, they will both have gone around once, right? Their angular velocity, their rate of rotation is the same. Those are really wonky circles. Pretend they're perfect, all right? Now, that's the first thing. So, okay, let me just say this though. As you can see, the speed that these are actually traveling is gonna be different based on the radius, right? This one, to go around one rotation, this one is gonna go a little slower. This one's gonna have to go much faster in order to get around at the same time as this point, right? This all ties into orbital mechanics and how astronautical engineers plot space travel, is they have to take this into account. If you have a lower orbit, you're actually going slower. A higher orbit means you're going faster. But that's not the angular velocity. What we're talking about when we talk about the fact that the one farther out goes faster, that is what we call linear velocity. I don't entirely understand how these words were chosen, linear and angular, but just work with me that they mean the same thing. Linear velocity means the rate of travel. And that's what we were saying. P and Q have the same rate of rotation because one time around is one time around, but they have a different rate of travel because Q is having to hustle way more to get all the way around to his bigger circle than little P who's putzing along on a smaller circle. The variable we use for linear velocity is a v, and we have a formula to calculate that. For these, we use rates. For this, we say that linear velocity is equal to the radius times the angular velocity. Okay, so that's what I was saying, is that this idea takes into account how far they are from the circle, and the one that's farther out is going faster. That's why we multiply the angular velocity, which we said is the same, times the radius, which is going to take into account that one's farther out than the other. So let me just identify this. This r stands for the radius. That's easy. You know what a radius is and how to measure it and all that. That's simple. This is the angular velocity, which is obvious because I told you that this omega is what we use to stand for that. But here's the trick. The angular velocity must be stated as radians over a unit of time, as I highlighted here. It doesn't matter which unit of time, but we have to use the unit of radians, not revolutions and not degrees. We have to use this in order to do this calculation. So now you can see why we practiced the unit multiplier thing, because if John gives us any one of these rates, we're going to have to convert it to this. All right? So this matches to what I was saying up there. Okay? Now let me give you a couple pieces of information that are going to help. I'm going to squeeze them. I don't like squeezing. I'm going to go to the next page. No, I'm going to put it all on here. Ready? Pi rads equals 180 degrees. Oh, we know that. We've seen that before, right? So 2 pi rads equals 360 degrees. Again, no newsflash, right? This is all good to know. Here comes the third one. 2 pi rads also equals 1 revolution. Okay, so if we're given a rate of rotation in degrees or in revolutions, here are some equivalent units that will allow us to translate as we need to, okay? We know that pi radians equals 180, so we just use that to build, okay, these are 3 different ways of saying a full circle, and we'll be able to use this information as we're converting our units. All right, I've now given you enough information to be dangerous. All of this is a giant puffy cloud of knowledge, and we're going to dive into a problem. All right? Here we go. My feeling is that these problems are complicated and difficult, very challenging, but man, you're gonna feel so smart. Example, and you're like, I don't wanna feel smart. I'm perfectly happy feeling the intelligence level that I am. But it's okay, we'll have fun. The wheel of a wagon has a radius of 14 inches. Okay, I'm just gonna draw a little picture here. Not necessary, but you know me, love the picture. It has a radius of 14 inches. I'm just gonna write here, R equals 14. And it's revolving at 40 revolutions per minute. Okay, 40 revolutions per minute. And my brain, here I have another set of our notes here that I can refer to. And I see, oh look, that's one of the other measures of angular velocity. It's measuring the rate of rotation. So this, I can see this equals angular velocity, right? Whenever I see one of these rates, I know that's what it is. And so I set it equal to omega. All right. How fast is the wagon moving in miles per hour? Now, I just want to tell you this. Whenever you see the words how fast, that means that you're supposed to find the linear velocity. Okay, that's how you can tell them apart. Angular velocity is a rate. How fast is linear velocity? It's a speed or a rate of travel. All right? So, and we want to know, okay, so linear velocity is what we're trying to find. So we're trying to find V in miles per hour. That's how we want to state our answer. Okay, well, let's figure out what we know. We know this formula. The linear velocity is equal to the radius times the angular velocity, but this has to be in rads. Okay? Rads are really good at measuring revolutions of things. This is a perfect example. So what we need to do is we need to convert the revolutions per minute to rads, okay? And we can do rads per minute, rads per second. The unit of time isn't important, so we'll just leave it as minutes. Oh, I'm sorry, I wrote the same thing. We need to change it to radians per minute. Okay, so we'll do that. It's 40 revolutions per minute, and we want to change it to rads per minute. Okay, all we have to do is adjust the top. Now, we have to figure out what is the connection between revolutions and radians, and it's right back here. Move it up a little bit. 2 pi rads equals 1 revolution. So we'll use that to make a little unit multiplier here. 2 pi rads equals 1 revolution. That is our unit multiplier that will help us get from revolutions to rads. And that's all we need to do, right? Then we'll be there. Okay, so these cancel and we multiply through and we get 80 pi, whoops, I almost wrote percentage, 80 pi rads per minute is the same angular velocity, the same rate as we originally had. We just changed it so it's stated in rads. Because that's what you have to do in order to use this formula. Okay, so now we're going to actually calculate the linear velocity, the speed, which will be equal to the radius times the angular velocity. And this isn't too terrible in the first step, right? So we'll take V equals the radius of 14, and we'll multiply it by the linear velocity, the angular velocity measured in rads times 80 pi, whoops, not like that, rads per minute. Okay, so that's all right, but now we have to change it from radians per minute to miles per hour. So we have to do another unit calculation. So let me take this up to the top of the next page. So it was 14, that's the radius, times 80 pi rads per minute, and we need to change that to miles per hour. Okay. And this is where it can get quite interesting. Oh, this is 42 inches. Sorry, that's why I'm missing it. All right, so first we're gonna get rid of this inches. So we're gonna take, because we wanna go to miles, right? We wanna go to miles per hour. So here comes a unit multiplier. We're gonna do inches to feet. And then we're gonna do feet to miles, right? Inches to feet, let's see, there's 12 inches in 1 foot, that cancels. Then we'll do 5280 in 1 mile. Now the feet cancel and we've achieved the top. Now we need to fix our bottom calculation, or our bottom unit rather. We need to go, I didn't write this, we're going from inches to feet, and we're going from feet to miles. And now here we'll do the time, and we just need to go from minutes to hours. That's relatively simple, right? Minutes are on the bottom, so we need minutes on the top to cancel. Hours, there's 60 minutes in 1 hour. The minutes cancel and we're left with hours, which is exactly what we want. Okay, so everything looks good. We've adjusted both of our units. The only problem left is, what do we do with this rads? What's that doing? How do we deal with that? And this is where I need to blow your mind into some little pieces. So, you know, get the vacuum handy, or at least a whisk broom, because this is gonna blow your mind a little bit. The unit of radians really has no meaning. We can take radians out and put radians in as we see fit. Does that confuse you? It's very confusing. After you do it for a while, you'll get a stronger sense of when you can't, how you play with that in and out. But in this problem, we can simply strike the radians from the problem, and we don't have to consider them any further. Does that confuse you? It's very confusing. Here's what it says. Radian measure is dimensionless. What? It doesn't have a dimension. It's not a length or a unit of time. And the unit radian is used as a convenience. Convenience to who? I don't know. Thus, the unit radian can be inserted or deleted as is convenient. What? This is difficult to understand at first. And practice with this concept is necessary. Okay, so what I'm going to tell you is that when we're doing this linear velocity calculation, you will just be able to strike that. The length unit comes here, the time unit comes here, radians is no longer necessary, and we just whack it. So now we can say that the linear velocity of this wagon wheel of ours is 14 times 80 pi, the ones we can ignore, times 60, right, over 12 times 5280 and another 1. And then our ending unit is miles per hour. And let me double check to make sure that's right. 14. Yes, this is correct. Holy cow, do you feel smart? This is a calculation of the rate of travel of that wagon wheel. Not how fast it's spinning. That's what we figured out first. It's spinning 80 pi rads per minute. But because it's 14 inches long, we know that this is its speed. It's 14 inches in radius. 14 inches long doesn't sound quite right, right? So this accounts for the size of the wheel. This accounts for the rate of rotation. We put them together to find the actual speed. Wow. And that was so fun, we're gonna do it again. And a third time, because, you know, actually it helps you guys, it helps so much to do multiple examples, because the first time through we're all just like, you know, digging in our nails and trying not to fall off the cliff, right? Oh, actually we only have to do one more. That was number 2, because we did that unit multiplier first. All right, example 53.3. We're not gonna build on this a whole lot, but like I said, this is a really classic physics calculation, and it comes up in applied physics as well. Like this would be something that would come up in astronomy, and like I said, any kind of engineering thing involving travel, especially like orbital mechanics, ooh, because we're going around in circles. It's super interesting to me. It's interesting to me how these mathematical concepts play out in science. I don't necessarily need to be the scientist, but I love that they do things, they explain the world. It's not just random things on pages. An automobile whose wheels are 30 inches in diameter. Oh, let me draw a picture though. Here's the automobile, it's in diameter. The diameter equals 30. We don't need the diameter, we need the radius. And that would be half, right? This is the number I need. And it's traveling at 40 miles per hour. Now John writes it out as 40 mph. We don't like this presentation in these problems. We want to write it as a fraction because we want to be very clear it's a rate. So we're going to say, oh, that is our angular velocity, and it equals 40 miles per hour. This is how it's useful to us. What is the angular velocity of the wheel? So we're supposed to find the angular velocity in revolutions per second. No, I'm wrong. This is the other one. Just a second. Find angular velocity in revolutions per second. If it's a speed, then it's this kind. How fast, right? Linear. This helps me so much. Linear velocity solves the question of how fast. This is a speed or a rate of travel. So this time what we're doing is we're taking our beautiful equation here, right? And we're saying, oh, we've got the linear velocity and we've got the radius. We're going to back into it and we're going to find this one, the angular velocity, and then we're going to make sure it's written in this format. Are you ready? Okay. So what we can do is restate this because we're trying to find W, right? So if we divide both sides by R, we can get omega equals V over R. Okay? Now, we know that we can put the numbers that we have into this. We know that our linear velocity is 40 miles per hour, because that's right there. And then we want to divide it by the radius, and we know the radius is 15 And what's our unit on that? Inches. Okay. Now the length measurements have to match. So what we're going to do here, we're going to convert the inches to miles or the miles to inches. We can do it either way. Let's convert the miles to inches. And what we want to do is we want to get rid of this denominator here. And I don't remember if you remember doing this from rate problems, but essentially what we're going to do is we're going to multiply top and bottom by the unit of hours. Oh, that's such a weird idea. But we'd rather be multiplying units down here than being dividing. That's too confusing. So what we do is we multiply top and bottom just by the unit, not by a number, just by the unit. This now cancels, and we say that our linear velocity is 40 miles per 15 inch hours. Is that weird enough for you? It's very weird for me. Let's take that to the top of the next page, and then what we're going to have to do is convert that so that the distances are the same. Okay, so we have that our linear velocity is equal to 40 miles per 15 inch hours. This is weird, but it's preferable to having the fraction of units in there. Okay, so we want to convert this into, no, we want to convert the miles into inches is what we decided to do. You could do it either way, but let's do this. We'll convert here. We'll go from miles to feet. That's an F. And then we'll go from feet to inches. Okay, so let's do that. Miles to feet, we'll put a mile down here, we'll put a foot up here. 1 mile is 50 to 80 feet. Now the miles have canceled. Feet go here, inches here, 1 foot, 12 inches. Cancel, cancel. Okay, so now we have written it as everything's in inches and hours, but John wants it to be in revolutions per second. So let's take care of the seconds first, and then we will do the last bit. I'm going to squeeze 2 time multipliers in here. They don't have to be written this way, but we're going to go from hours to minutes in the first box, and then in the second box we're going to go minutes to seconds. All right, so again, I'm going upside down now. I'm in hours here, so I want my hour up here and my minute down here, 1 in 60, and then the same thing will happen here. I will have minutes and seconds. I know I'm really squishing here, 1 and 60. So hours cancels and minutes cancel. Okay, so let's get this much simplified, and then we'll deal with one more piece of it. All right, so I'm going to gather up all these numbers and straighten up my units. It's going to be 40 times 5280 times 12 over 15 times 1 times 1 times 60 times 60. And this is per seconds. And here comes the weird part. The inches cancel, right? Because we have inches on the top and inches on the bottom, right? After we turned this miles, we canceled it here and then we canceled it here. We ended up with inches, but we also have inches in our denominator. So these cancel, and here comes one of those weird moments. We just write radians. Are you kidding me? That is so weird, right? But that's what we can do, all right? That is something that you might need to check the solutions manual on, is when can you put it in and when can you take it out. As long, like in this case, I could see I've got inches and inches, they cancel. That's a great moment, but I don't know what to do, right? What's my unit on my top? So that's a great moment to say, I need to look at the solutions manual and see at this point, what should my top unit be? And then you'll see the radians and you'll say, oh, good Lord. We just drop it in. We just say, well, we don't have another unit, so we better put in radians. That's crazy. Now, what we're trying to do in our final step, though, is we're trying to convert this into revolutions per second, right? I'm going to write that here. That's how John wants the ending units to be calculated. Convert to revolutions per second. Okay, we've already got the seconds worked out, right? And so now all we have to do is remember how many radians are in one revolution. Well, my brain can do that because I know that 180 degrees equals pi radians. So the full circle, which would be 360 degrees, is 2 pi rads. And 360 equals 1 full revolution. This is what I wrote on the first page, and I'm writing it again to help you. Okay, so if we've got this in radians and we want to convert it to revolutions, we know that 2 pi rads equals 1 revolution. So I'm going to do one more unit multiplier. And in this one, I want to put rads down here, and I want to put revolutions up here. This is going to be going from rads to revs. And I use this information. 1 revolution equals 2 pi rads. This cancels. Now I've got both of my units exactly how I want. If you have a headache at this point, I don't blame you. And now I'm just going to rewrite this one last time to make it beautiful. The angular velocity is equal to 40 times 5280, I'm kind of squishing, times 12, I don't need the 1, over 15, I'll do 60 squared here so I save a little space, times 2 pi, and my units are revolutions per second. Again, I like to write that out because if I just put the S, I'm skunked. Let me look. 40, 52, 80, 12, 15, 60, 60, 2 pi. Yay! You guys, that was such a hard problem. If you're whimpering a little bit and you just want to run away from me and go outside and climb a tree, I understand. Go do it. We're done with this lesson. We're not going to build on this, but you will be doing these problems in the homework, but we're not going to make this worse than it already is. That's a super hard lesson, and if you are even clinging to a semblance of sanity right now, you're way ahead of the game. So be patient with yourself, work those through, keep this page close to you as you're trying to work these problems so that you have the formulas and the words in front of you. Sometimes I think that's the hardest part, is just keeping straight all the terminology and what it is that we're trying to do. And then this whole crazy unit multiplier business turns these into a mess. which is why we've practiced unit multipliers for so long. You thought this was just ridiculous that we were making such a big deal out of them. Now you know why we've obsessed over these things, because they're really complicated to use in these kind of problems. Okay, I'm done talking. Seriously, go give yourself a break. Do not leap into schoolwork or something difficult right now. Go have a drink of water, go outside, take at least a 10-minute break. And I will see you soon for lesson 54. Thank you, goodbye.